Hello, welcome to the class. The concept today that we are going to start is with the concept known as equations of state for real gases, also known as the van der Waals equation. Now, the chapter that we are doing is states of matter, gases, and liquids. And we had already done the equation of states for the ideal gas, and we also studied about the kinetic theory of gas, and also studied the deviation that the real gas shows with the ideal behavior. Now, when this deviation was created by the ideal real gas during the observation of the ideal behaviors, those deviation was attributed in the ideal gas equation. Now, the ideal gas equation we had studied, and the equation of ideal gas is saying that PV equals to nRT, where P is the pressure of an ideal gas, V is the volume of the ideal gas, S is the n numbers of mole of the ideal gas under observation, R is the universal gas constant, and T is the temperature of the temperature at which the observation is happening. Now, this is the equation of state for ideal gas. Now, this equation of state or the gas laws was observed on the basis of the kinetic theory of gas. In the kinetic theory of gas, two assumptions were made: that the intermolecular forces of attraction and repulsion between the particles, between the constituent particles, between the constituent molecules of gas do not exist. That is, the intermolecular attraction or intermolecular repulsion is zero in the constituent particles, in the constituent molecules of the gas particles. Now, this assumption it is in the violation for the real gases, because it has been observed that in real gas the intermolecular forces of attraction or intermolecular force of repulsion do exist. Now, what happened when a particle, when a constituent particle resides within a bulk in the gas molecule? Supposedly this is the container. A molecule is present in the bulk of the container. Now, in the bulk of the container, the molecule is surrounded by the other molecule, and it is attracted or repelled by the other molecule in all direction. As a result, the net attraction or the net repulsion force on this particular particle becomes zero. So, the particle, the constituent particle of real gas residing in the bulk do not as such feel a net force. So, the kinetic theory of gas in considerable amount is true for constant particle in the bulk for real gas, but when a particle, constant particle, is nearer to the wall of the container, at that situation this particle is feeling attraction or repulsion force, is feeling a force from the surrounding particles towards the surrounding particle. A pull is being felt by this particle that is nearer to the wall. Now, during the collision of the constant particle, when the constant particle of real gas collide with the wall of the container, it is giving rise to the pressure of the gas. As in the kinetic theory of gas, no attraction force was considered. The pressure that we were getting for the ideal gas was higher compared to the real gas, compared to the real phenomena, because in real gas, in nature, when the molecule or the particle, constant molecule of the real gas collide with the container wall, it is facing a pull by the surrounding particle. As a result, it cannot rise as much amount of pressure as the ideal gas. So the pressure of the gas in the ideal gas law, in the ideal equation of in the equation of state for ideal gas, that was considered, in fact, that amount of pressure for real gas is less. So a modification in the pressure gradient is required in the equation of state. Similarly, the volume of the entire gas was assumed to be the entire container's volume, because in the kinetic theory of gas, the volume of the individual particle, individual constituent gas molecule, was considered to be negligible. That's compared to the entire volume of the container. That's why it was taken, it was negligible and it was neglected during the observation. So the volume of the gas during the observation for ideal gas was taken as the entire volume of the container. But in real life, the volume of the constant particle is in the considerable amount. It cannot be neglected. That's why it has been found that a particular gas particle do occupy a certain amount of volume of the container. As a result, the entire molecule or the entire constituent molecule of gas occupy this portion of the occupy a portion of the volume of the container, and the remaining free space, a remaining free volume, is available for the free motion of the particle, constant gas particle. Now the volume gradient in the equation of state is the volume that is available for the free motion of the gas. That was in the kinetic theory of gas, was considered that as the constant particles volume was neglected, so the entire volume of the container is the volume of the gas, because the entire volume of the container is free for the free motion of the particle, which is not true. In for real gas in nature, the amount of the volume that is available for free motion of the gas is the total volume of the container minus the volume of the minus the volume that the real gas occupies. So volume correction is also required in the equation of state. After this pressure correction and volume correction done, this correction was done by van der Waals, and he gave equation of state for real gas. In other word, this equation of state of real gas, also known as the van der Waals equation, and this expression is P plus n square A by V square whole into V minus NB equals to nRT. This expression is known as the equation of state for real gas. For n moles of real gas. For 1 mole of real gas, this equation of state becomes P plus A by V square whole into V minus B equals to RT. This expression is equation of state for real gas, for 1 mole of real gas. Now this n square A by V square, or for this 1 mole of real gas, A by V square is known as the pressure correction factor, and this V minus B, this B is known as the volume correction factor. Real gases, which shows the deviation was explained on the basis of this expression, real gas expression, of van der Waals gas expression. This deviation was created due to two assumptions that was included in the kinetic theory of gas, on which the gas laws was developed. The first one was that the pressure of the gas was arising due to the collision of the constant particle with the wall of the container. As no intermolecular forces of attraction was considered, there was higher amount of pressure that was that was being assumed for the ideal gas compared to the real gas. And another assumption that was taken, that the entire volume of the particle was neglected, entire volume of the constituent molecule of gases were neglected in the real gas. In fact, the entire volume of the container was considered to be the entire volume of the gas. That's why the pressure was needed, pressure were and the volume both were corrected, and this expression was established after this correction. The last time we studied the deviation of the real gas from the ideal behavior, we studied that with the help of a plot. The plot that we take help for this study was the PV versus pressure plot. Now this PV versus PV plot, in this PV versus PV plot, if ideal behavior is considered, the curve that we get is a straight line curve parallel to pressure axis. But if we try to draw the curve for the real gases, we get two sets of curve. The one set of curve look like this. This type of curve, this set of curve is given by gases like nitrogen, oxygen, methane, these kind of gases. Let's study the behavior of this kind of gases with the help of this van der Waals equation and study this curve. Case 1. As the pressure curve starts from 0 and then keep on increasing, we are going to consider the first case when the pressure is very low. We know that the volume of the gas is inversely proportional with the pressure of the gas. As pressure is very low, the volume is going to be very high. As volume is very high, the magnitude of volume will be very high compared to the magnitude of B, the pressure correction factor. The volume magnitude of pressure correction factor will be negligible, will become negligible compared to the magnitude of the volume. This will result in V minus B is almost equals to V. So the van der Waals equation will be modified to P plus A by V square whole into V equals to RT, or PV plus A by V equals to RT, or PV equals to RT minus A by V. Now the straight line curve, PV curve, for parallel to P axis for real gas was drawn on the basis of the expression PV equals to RT, which is the states of equation for ideal gas. The real gas at low pressure range, the van der Waals equation is giving PV equals to RT minus A by V. which implying that at the low pressure range for a particular pressure, the magnitude of PV for real gas is less compared to the ideal gas. And also is saying that with the increase in the pressure at the low pressure range, the PV value will keep on decreasing. Now this equation is evident in the low pressure range in the graph, where at the lower pressure range we are seeing that with the increase in the pressure, the PV curve is decreasing till a point. Then at the higher pressure range, with the increase in the pressure, the PV value is increasing, which is we are going to study in the case number 2. When the pressure is very high, the volume will be very low. Now, as the volume is very low, the magnitude of the volume correction factor B cannot be neglected. But the pressure correction factor, the magnitude of pressure correction factor become excessively low compared to the magnitude of the pressure. That is, it becomes negligible compared to the magnitude of the pressure. That is, A by V square, the magnitude of pressure correction factor become negligible compared to the magnitude of pressure. That's why the P plus A by V square, this term becomes almost equals to P. So the modified van der Waals equation will look like P whole into V minus B equals to RT, or PV minus PB equals to RT, or PV equals to RT plus PB. That is, at higher pressure region, the magnitude of PV for real gas is higher compared to the ideal gas. Not only that, with the increase in the pressure, the magnitude keep on increasing. Now, this is the case that is that can be seen in the curve. In this higher pressure region, we are seeing that with the increase in the pressure is keep on increasing, and in this higher pressure region, the pressure after this point, the pressure exceeds the actual ideal value. Now, this entire set is for gases like nitrogen, oxygen and methane, but there is a second set of curve that we got. That second set is this one, a straight line but not coinciding with the parallel line of ideal gas, parallel line of ideal gas. This straight line, this set of curve was given by hydrogen helium like gas. We are going to study that this deviation for the hydrogen and the helium gas in the case number 3. For hydrogen helium like gases. Now, hydrogen helium, the constant particle or molecules of hydrogen helium gases are extremely small. It has been found that the intermolecular forces of attraction in these particles are extremely negligible. That's why the pressure correction factor value becomes negligible compared to the pressure at any range of pressure. The intermolecular force is very low for this kind of gases. Therefore, the a magnitude of A by V square become very negligible compared to the pressure value for for any range of pressure. This will result in P plus A by V square almost equals to P for any range of pressure. So for hydrogen and helium gas, the van der Waals equation becomes P whole into V minus B equals to RT, which results in PV minus PB equals to RT, or PV equals to RT plus PB. This results in This implies that for any value of pressure, the PV value for hydrogen or helium like gases will be always more than the ideal value, and it will always increase in a regular manner with the increase in the pressure.